Hey, Tara. Did you have a good Easter?
We didn't do anything.
Yeah, neither did I.
But I mean, overall, it was good. I got to watch some TV.
Yeah. I got your quiz, so that's good, I guess. We'll see. Hey, Dion.
Hey.
And Tara says, hey. Oh, there comes Deborah. All right, let's see. Third week. After this week, we'll be half through. I'm just counting. I'm just counting. Just like you are.
Counting with you.
All right, up. Here comes the other D. That'll be Deborah. Let's see what I got here. I'm gonna go ahead and share the screen, guys. Who I got? Alexis. Did y'all get asked for a password, by the way?
Yes.
Okay. I just emailed it back out because I completely forgot it. They asked me for one this morning, and I was just like, oh my God, I don't know where it is. So
I just copied and pasted from the first email you sent.
Yeah, that's a good idea. That's definitely what you need to do. All right, let me share my screen here. I don't know why they keep asking me that. Sharing is paused. All right. Let's see, we got what we got.
Hey, Deborah.
Hello.
Hey, Deborah. Where's Alexa? I want her to be the first one here tomorrow. Okay. Guys, let me tell you, I thought I put it on here and the new assignment sheet on here, but it's on Moodle. I definitely got it on Moodle. Let me see if I got it on here. I could show you something here. I don't think I put it on here. Yeah, it's all right. I didn't put it on there, but what we're doing, I'm going to finish up what I started on sequences Thursday or Friday, whenever it was. Oh no, we didn't have class Friday, Thursday. And there's some new homework that I've assigned that'll take care of, you'll finish up everything that was in the section and a few extra things that I wrote on there. So be sure you look on Moodle for the homework, not necessarily just the video, because I added a few things. And then tomorrow and Wednesday, we're going to be working on another section. It was going to take a couple of days to do that. And that's all I got sort of planned at this point. We've got a little further to go before we have another test. I'm not worried about that yet. Y'all have already had 3, so that's working out fine schedule wise. I forgot what I was gonna say. Oh well, anyway, let me kind of run back over what I did in that while we're waiting for Alexis, what I did on Thursday, and then pick it up kind of where I left off. I'm gonna go ahead and do that. There she is. Well, let her in. Should I let her in? Should I take a vote? Okay, whatever. Birds are singing. Whose birds are singing? Okay, they're outside Deborah's windows. Birds are singing. So things are normal, sort of, outside. Anyway, hi, Alexis. She's connecting to the audio. She's not. You there, Alexis, yet? Okay.
I just don't remember the password to this thing. So
I know. Tell her what you did, Tiara.
I just copy and paste.
wait, copy and paste what?
Password.
Where'd you paste it into?
Yeah,
My
I don't
notes.
know.
Okay. She's pasting it into her notes. I make you feel a little less bad, Alexis. I logged on this morning. It asked me the password and I couldn't find it. I was scrambling, so I had to go back to an email. What I did today, guys, just to make sure everybody got it, is right before class, I emailed it to everybody. So did you get that email or did you find it, Alexis?
Oh, I just saw, I was looking I was trying to find the old emails.
Yeah.
And then when I scrolled up, it was there. I was scrolling.
Okay,
You know.
all right. That's what I did basically to find it in a panic. So anyway, so what I was saying is that online is a new assignment sheet. It takes us through basically through Wednesday, and then we'll figure out where we're going to go from there. I've got to do some pasting and cutting myself of some of the things I would have normally done during the semester to make sure we hit the highlights and the things we really need to look at. So so look at that. The homework will have changed a little bit because what I'm going to do today is finish up what I wanted to do, what I would have done Friday, which we had the day off. So I'll still be working in 11.1. So I'm going to go to 11.1, and I'm going to see if I can get it back up. I'm going to go to 11.1 and just sort of run over what I did, and then finish up what I had intended to do. What we did in 11.1 was introduce the idea of a sequence, and it's just a collection of real numbers. It's just like a list of numbers, and ultimately what we wanted to do was see if the limit of this list existed. And when we had all our old limit rules and so forth to do that, and I'm going to add a few things to it today to help us do that. We talked about what happened when you had -1 to the nth, and that these were just points and not full graphs. It made the sign alternate when we had -1. We would look at something like this, and if we wanted to say what's the limit of this sequence as n goes to infinity. That's an easy one, guys. You know, it's a polynomials one over the other, and we had a theorem that said this works just like the function x over x plus 1. So if you remember from Calc 1, we would put a 1 here and a 1 here, and it turned out to be 1. And we could see that. You could see that when we were looking at all the different terms of this thing. Each one's called a term. This nth term here tells me how I build the sequence. The other kind of sequence we talked about was a recursive sequence. I put a recursive sequence on your homework. It may be a different one from what I put on the original one, but you just got more practice. It's where you start with 1, you start with something. Maybe you start with 2. We talked about Fibonacci sequence. And then you found the next one by plugging in the one that you had before. So if I wanted to find A2, I would let K be 1, and A2 would be 2 times A1, and I know A1 is 3. And you just keep going doing that. Is everybody okay on recursive sequences? And that wasn't so bad. We talked again about sort of what the limit meant. If the limit here was, this one was bouncing around because we had this -1/2 to a power, which would have been plus sometimes and negative sometimes. So even though it bounced around, eventually it was getting closer and closer to 2, which meant that I could make it as close to 2 as I wanted. And that was my formal definition of the limit of a sequence, which we talked a little bit about that. We typically will use this stuff only in proofs for right now, but that was sort of the standard definition of what it meant for a sequence to have a limit. And it basically means that if you go far enough out in the sequence, you can make the difference between that term and what you're saying the limit is as small as you want. And that epsilon was a number no matter how small. The notation going to infinity just means you can make it no matter how big. You can make it as big as, whatever you say. It's going to go to infinity if it can be made of what we call arbitrarily large. Here, let's see, same few more examples. Talking about how things can diverge. And when the limit doesn't exist, we say it diverges. When it converges, that means the limit does exist. This one right here just bounced back and forth. It was not getting closer and closer to anything. It was just hanging around here, but always the same distance away. It wasn't getting closer to anything. So we would say that the limit does not exist there. It oscillates. So that would mean it diverges. You can use L'Hopital's rule on these things because that's another way to find a limit. So we use L'Hopital's rule on a few of them. Here's sort of where I stopped right here. I made a new lecture starting with this. So let me get back to that one and we'll pick up there and we'll start new with that. So here's 11.1 continued. Let's make sure I got all that. Okay, here we go. So, questions to anybody about in general what we're doing? We're not looking at any integrals here. We won't be well. I don't know if we'll be there is a way to use some integrals in this stuff, but we probably won't do that. Here's the first theorem I want to talk about. It says that the limit as n goes to infinity of r to a power is 0 if the absolute value of r is less than 1. I'm going to give you some examples, but remember from algebra, the absolute value of a number is less than 1 if that number is between -1 and 1. Okay? So I'll give you an example in a minute. If we have the limit as n goes to infinity, the absolute value of Rn, that's equal to infinity if the absolute value of r is bigger than 1. Again, we'll talk about why this happens, but remember what that means from algebra, from your encounters with absolute value. If you look at a real number line, and you look at the number -1 and 1, anything, this says right here, anything in between -1 and 1 is going to have an absolute value less than 1. If I took a half, the absolute value of a half is less than 1. If I took minus a half, absolute value of minus a half is less than 1. So this refers to absolute value of r less than 1. Anything between 1 and -1. On the other hand, if we have something out here, in other words, absolute value of r bigger than 1, that means the absolute value of r is going to be bigger than 1 if you're already bigger than 1 or if you're less than -1. Because for example, if you pick -2, the absolute value of -2 is 2. That's clearly bigger than 1. So that's what we're looking at right there. And we put it in absolute value because this thing could bounce around. It could have positive and negative value. So let me give you a bunch of examples here, and we'll see what happens. So keep that theorem in mind. If the r that you're raising to the power is between 1 and -1 on the way to infinity, for n, it's equal to 0. If its absolute value is bigger than 1, it goes to infinity. All right, so let's look at this. So look at this first example. -2/3 to the nth. If we look at some terms of that sequence, if you let n be 1, it's -2/3. If you let n be 2, it's 4/9. Bouncing around because of that minus sign in there. This next one will be -8/27. If you let it be 4, it'll be 16/81. If you were to look at the decimal values there, what you'd see is that this was getting to be a smaller and smaller fraction. The denominator is getting big relative to the numerator. So for instance, relative to 4/9 is a little less than a half. This is clearly a lot less than a half. But notice, the reason this thing we know it goes to 0, the r that you're raising to that power is -2/3. The absolute value of -2/3 is 2/3. That's less than 1. That little theorem we looked at tells us that that one's going to go to 0. So that's an example of that. If you look at something like this, that might throw you off, guys, a little bit there, but sometimes you'll see something that's written like that and you need to rewrite it. So if this is 2 to the nth over 3 to the nth, that's the same thing as 2/3 to the nth. Of course, you know you raise the numerator and the denominator to that power. R is 2/3. Absolute value of r is less than 1. Therefore, the limit of this thing goes to 0 as well because r is 2/3. Absolute value 2/3 less than 1. Look at this one. R is 1/2. R is a half. Absolute value of a half is less than 1. That one goes to 0. Okay? So I'm just looking at what gets raised to the power there. What happens when you raise a fraction to a power that's less than 1 is the denominator gets big faster than the numerator does. All right, look at this one. Pretty clear that if I looked at 2 to the nth, some pieces of the sequence, or the sequence would be 2, 4, 2 cubed is 8, 2 to the 4th is 16. It's pretty clear that there's nothing to keep that from getting bigger and bigger. Notice that the thing you're raising to the power is 2. That means your r is 2. Absolute value is 2 is bigger than 1. So 2 bigger than 1. That means this thing is going to infinity. Okay. You didn't have that to use on your homework over the weekend, so you may have run into some things maybe that you didn't know what to do with, okay? Because this is not something you could use L'Hopital's rule on, but it's pretty clear it is going to infinity. If you look at this one, R is -3. Absolute value of -3 is 3, and 3 is bigger than 1. That tells me that one's going to go to infinity. All right, and you can see that if you looked at some things in this sequence, -3, 9, -27, 81. It's bouncing around, but it's getting bigger and bigger, bigger negatively and bigger positively. So that thing right there is going to infinity. This was a little bit of a trick. Not really a trick, but you'll sort of see what happens. If you look at 1.01, the R is 1.01. The absolute value of R is big 1.01, and it's bigger than 1. That thing's going to go to infinity. If you plugged in values for n to get the pieces of the sequence, you get 1.01, 1.0201, 1.03, 0301. It's not getting bigger faster, but it's definitely getting bigger. All right. So that thing eventually is going to go to infinity. You might have to go a long ways out in the sequence to see that, but it's definitely going to go. I mean, if you went to 3 trillion, this thing is, you'll see it getting big. And that's what our definition said about what it meant for a sequence to go to infinity. It says no matter how big a number you pick, if you go far enough out in this sequence, you can get bigger than that number. So it's going to infinity. Okay, questions about that, anybody? We're going to use that in a lot of different ways. All right, so the next thing I want to look at is something I think we did this in Calc 1, but sometimes I get in a hurry and I don't talk about it, but I'm going to talk about it now. It's something called the sandwich theorem for sequences. You guys remember me doing something about the sandwich theorem in Calc 1? Anybody remember? It was one where if you got a function stuck between 2 other functions and they had a particular limit and it went to the same thing, the ones on the ends, then it squeezed the one in the middle and it went to the same limit. That's the idea here. So here's what it says. If AN, BN, and CN are sequences, and every term BN is in between AN and CN, for every N, and if the limit of the one on the end goes to L, and the limit of the other one on that end also goes to L. So both of these, as you take the limit, are going to L, because all of those terms BN are in between, it squeezes it, and that limit also goes to L. So if you got something that's squeezed in between 2 things that are going to the same thing, what's in the middle is going to that thing. Here's where this came in handy. And I think we use an example just like this in Calc 1. Suppose we want to take the limit of cosine squared of n over 3 to the n. That's a little hard to deal with in terms, we could use L'Hopital's rule on it, but it just gets messier and messier. And anyway, I don't even know that cosine squared goes to infinity. This definitely is going to infinity. And I'm not sure about that thing. I don't think it's going to go to infinity because the cosine is always between what, guys? What values is a cosine always in between from trigonometry?
1 and -1.
Yeah, it's between 1 and -1. So because I've got this square on here, that kind of that interval gets a little bit shrunken. It just means the cosine squared would be between 0 and 1. So I'm going to write that right here. So sort of what we know about this top is that the cosine squared of n is always between 1 and 0. Again, that's just because we got the square there. If there were no square there, I'd put it between 1 and -1. Okay. So, so what we're trying to do is squeeze this sequence, this nth term of the sequence here, cosine squared over 3 to the nth, in between something I know where it goes. So the 3 to the nth gives me a hint. I'm going to write 1 over 3 to the nth, because basically all I did was I looked at this thing and I said, well, I'm interested in cosine squared over 3 to the nth. So I'm just going to divide everything by 3 to the nth. So when I do that, I get 1 over 3 to the nth. I get cosine squared of n over 3 to the nth, which is what I'm interested in. And 0 over 3 to the nth is 0. But here's the nice thing about this. Look at this end. We just learned if we had a sequence that looked like an R raised to a power, if that R was less than 1, absolute value less than 1, then where was this one going, guys? Where would that one go if we get the 1/3 is in between 1 and -1?
0.
It went to 0. Yeah, we just learned that. And of course, the limit of 0 is 0. So because this cosine squared is squeezed in between those two things that are going to 0, its limit as n goes to infinity of cosine squared of n over 3 to the nth is also 0. It got squeezed in there. And so we would say it converged to 0. So the limit of that sequence. And that's about the only way we could get a handle on that right now. Again, I mentioned this a little earlier, but the limit theorems here are similar to the ones in chapter 2. In other words, from Calc 1, chapter 2 in our book. The limit of a sum is the sum of the limits, or the difference. The limit of a product is a product of the limits. The limit of a constant times a function, sorry, times a sequence is the constant times the limit of that sequence. And that's actually helpful sometimes too, guys. If you look at this little example I've got down here squeezed in, I said, what's the limit of 2, I said that, of 2 to the n plus 1? It actually, let me squeeze it in down here. It got cut off. But that would be the limit. That would be the limit of 2 times 2 to the n. And I know that the limit of a constant times a function, I can pull the constant out. So that's the limit as n goes to infinity of 2 to the n. And again, we just learned, and it was easy to see, that if we're going to infinity, where's 2 to the nth going? It's because that R is bigger than 1, it's definitely going to infinity. So 2 times infinity is still just infinity. Okay.
Can you go up a little bit so we can write that down?
Oh, I'm sorry. I've come, let me see. Come this way, Alexis?
Yeah, right there.
Okay, all right. So those look like all those limit theorems that we had. Now, again, things got cut off here, so I'm sorry. I'll try to write it all over again. All I did was break this apart. There's the 2 to the first and 2 to the nth. On this one, I might have something like, let me put it down here, guys. I could cut it off. I don't know. I took a bad scan. Suppose I said, what's the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n? Got to be a little bit sneaky here, because if you rewrite this, 2 to the n plus 1 is 2 to the n, or 2 times 2 to the n. Notice, like bases, I add powers, over 3 to the n. I can bring the 2 out. Let me go up here. I can bring the 2 out, and then I'll have 2/3 to the n that I'm taking the limit as n goes to infinity of. And again, because that 2/3, the absolute value is less than 1, this will be 2 times 0, because that'll be going to 0, and I'll get 0. So you can make it fit into that theorem we just did if you break it apart a little bit. Okay, is that okay? Does anybody need to see any more of it? Okay.
I'm good now.
Good? Okay. All right, let's look at this next piece. This next piece says, let an be a sequence if the limit of the absolute value of an equals 0, then the limit of an equals 0. Now, guys, this is to take care of all those things that bounce around, but still are getting closer and closer to something. And it's what it's telling you is all you have to look at is the absolute value, okay? In other words, if the absolute value goes to 0, then the limit itself will go to 0. So for instance, look at this one. I have an equal -1 to the n plus 1 over 1 over n. It looks like this. If I let n be 1, it'll be -1 squared, which is 1. And it's going to alternate because of this power right here. So it starts at 1. It goes down to -1/2. It starts at 1, goes down to -1/2, then it's -1/4, then it's -1/8. It's bouncing around, but what you see is that it is getting closer and closer to 0. So the absolute value of an is 1 over n. So we see that this thing out of absolute value is going to 0. So that says 1 over n goes to 0. That's pretty easy to see there. Well, we use that in special places too, but that's what that's all about. Okay, one other thing here. They didn't have any like these in your book, and I kind of like them because they make you figure out patterns in things. And I think that's a good thing to be able to do here. So what we're going to try to do here is we're going to, instead of being given an nth term and writing the elements of the sequence, I'm going to give you the elements of the sequence and tell me if you can give me what the nth term is. So it's looking at the pattern. So guys, cut your mics off and let's take a look at what you think the patterns are in these. And some of them are easy and some of them are harder. How about the first one? Now remember, I'm trying to write something so that when I plug in n equal 1, n equal 2, n equal 3, I get these numbers. So tell me what do you think the pattern is here? Look at the one thing you might want to do. Somebody say something? I couldn't hear it. What do you think the pattern is for 1, 8, 27, 81? Hmm. 1, 8. Deborah? I can't hear you.
Oh, I'm not saying anything.
Okay. Who else? What you think, Alexis? What you think, Alexis? Take your mic off. Look at the bottom numbers.
Yeah. I see.
Remember
27,
now,
81.
yeah, look, you were plugging in 1, 2, 3, 4. That's how you got the terms of the sequence, guys, by plugging in 1, 2, 3, 4. How do you think 1 is related to 1, 2 is related to 8, 3 is related to 27, 4 is related to 81?
Oh, n cubed.
N cubed, exactly. 8 is 2, 1 is 1 cubed, 8 is 2 cubed, 27 is 3 cubed, 81 is 4 cubed. I think this one right here is 1 over n cubed. So guys, you see what I'm trying to do? I'm trying to look at the sequence, look at the pattern and see if I can come up with that. So as n goes to infinity, where's this thing going right here?
0.
0. So I can kind of see that in the terms, but you see it there, it's pretty clear. Okay, let's look at this one. It's a string of 5s, but they alternate signs. So we know what makes things alternate. It's putting some power on -1. So think about the n again. For this one, you would have wanted to plug in 1, this one 2, this one 3, and we've got to make it alternate. The first one needs to be positive. So whatever power we need here, when we plug in 1, it needs to be even, because -1 to the even power would be positive. What do you think I could plug in there to make it alternate like that?
5.
The 5's already there. I've gotten the 5. What I don't have is the alternation part. Tell me what would happen if I put in n right there. What would happen if I put in n? Would it alternate right if I put in n? No, because if I put in 1 first, what would the first term of the sequence be?
Negative.
It'd be -5, and the next one would be +5, and so on. Everybody agree that n ain't gonna work? what's going to make it work? I mean, in a way, guys, it's off by 1.
N minus 1?
I could try N minus 1. I tell you, that's a really good guess. It's going to turn out that's not quite right, but I'm glad you said it, because what's going to happen is if I let N be 1, I would get, actually it is right. Okay, it's right. Well, I was going to say N plus 1, but it doesn't matter. If I let N be 1, I'll get minus 1 to the 0. And minus 1 to the 0 is, anything to the 0 is 1, so 1 times 5 is 5. Now, what if I put in 2 there? Does it give me minus 5? Yeah, 2 minus 1 is 1. Minus 1 to the 1 is minus 1 times 5 is 5. If I put in 3, it'll be minus 1 squared. So I get my positive 5. Okay, N minus 1 works. I was going to put in N plus 1. It doesn't, the answers can be different here, guys. So if I put in N plus 1, it would work the same way. Because if I put in N plus 1, I'd start with a square and it would still be positive.
I'm confused. So how would this, like, where's this N minus 1 going?
Well, that's what your sequence, that's how you generate your sequence, Alexis. Let me write it better. Minus 1 to the N minus 1 times 5. Suppose I said, I want you to,
That's why I was so confused, because I was like, okay.
you see what I'm saying? That was a bad slot there. If I start with N equal 1, I would get 5. N equal 2 would give me minus 5. Are you okay on generating those pieces?
No, I still don't know what I'm doing.
Okay, well, look at this one. Look at the first one. A sequence is something that looks like terms, A1, A2, A3, A4. And that tells you A1 is when you plug in 1 for N. So 1 over 1 cubed is 1. If I plug in 2 for N, 1 over 2 cubed is 1/8. It's like a function, but you're just plugging in whole numbers, okay? Whole positive numbers. If I plug in 3, I've got 1 over 3 cubed is 27. 1 over 3 to the 4th is 81. What's the next one in that one going to be, Alexis? Might need your calculator. 1 over what?
1 over, oh gosh. 1 over 5 cubed.
Okay, I heard it. I don't know what it is, but it's 1 over 5 cubed. I think that's 240. I don't know what it is. What is it? What's 5 cubed?
1 over 125.
Okay. Yeah, you're right. That's easy. Whatever. So the next one's 1 over 125. The next one will be 1 over 6 cubed. You see what I'm doing now? In that one?
I've never been really good at this sequence and stuff, so.
Well, and it's, some people are really good at seeing patterns and some people aren't so great at seeing patterns. I just want you to try it, okay? But I will say that what we learned from the second one is that we're getting all 5s. The only thing that's changing in the second one is that the signs are alternating. And if you want the signs to alternate, you put an N up there. If you want to start with N equal 1, N wouldn't have worked there because minus 1 to the first would have given me a minus 5 first. So that's why Tierra said, let's take away 1 and it'll give you the one before that. The one right before an odd number will be an even number, and that would have given me the positive here. So that's what that looks like. Now, if we try it, if I let N be 1, that's always the first term in the sequence. That's my A1. 1 minus 1 is 0. Minus 1 to the 0 is 1, and 1 times 5 is 5. If you let N be 2, 2 minus 1 is 1. Minus 1 to the first is minus 1 times 5 is minus 5. And then it alternates back and forth. That's what when you see an alternation of some sort, you're going to put minus 1 to some power and make it work. If N doesn't work, try N minus 1 or N plus 1. All right, let's look, I tell you what, let's look at D first. I don't want to look at C yet. Remember that what you're plugging in first is 1, 2, then 3, and then 4. And then 5, 6, 7, 8. Actually, I got a big hint about something here. If I want to get a 1, 2, when I'm plugging in 1, 2, 3, and 4, look at what the numerator was. 1, 2, 3, 4. So what do you think I'm going to let N be there? if I want to get 1, 2, 3, 4 up there.
The numerator.
The numerator, at which I would just be n, wouldn't it? Because if I plug in 1, it'll be 1 over something. If I plug in 2, it'll be 2 over something. If I plug in 3, it'll be 3 over something, and so on, 4 over something. So I should let it be n. That's a big hint in that problem. Now, here's the next hint. How is 1 related to 2 and 3? What's the kind of pattern there? 1, 2, 3, 2, 3, 4, 3, 4, 5. What's the pattern right here between these things?
N plus 1 times n plus 2.
Okay, 2 is 1 bigger than 1. So if I put n plus 1 down there, so Deborah said n plus 1. So if n were 1, n plus 1 would be 2. And then the next was just 1 more. So that'll be n plus 2. See if it works. If you plug in 4, you'd have 4 over 5 times 6. That's that one right there. And so on. Okay. Let's look at E. E is a little different, guys, because it's got something more than numbers in it. But that's okay. That's easy. Once again, when you plug 1 in, you should get this. When you plug 2 in, you should get that. 3 in, you should get that. 4 in, you should get that. Here are the kind of patterns I look for. I look for what I'm plugging in and the numbers that I get. So it looks like, let me write, and I just write down everything I can see about the function. Look at the denominator and look at the term. That's the second term. So when I plug in 2 here, I should get 1 less. When I plug in 3, I should get 1 less. When I plug in 4, I should get 1 less. When I plug in 1, I should just get 1. And these powers are the same as that base. X to the first, x to the second, x cubed. So it's going to be, let's just play with it here. It's going to be x to some power over some number that is the same. Yeah, that's the same, at least in these. I don't know about 1, but I'll show you what I'm going to do with 1. So 2 over 2, 3 over 3 is the fourth one. And it'll be over that same number, whatever the power is, because I've got x squared over x squared and x cubed over x cubed. So tell me, let's just look at this piece right here, because I'm going to show you something else I can do. Tell me what n I should put there if I want to get, at the second term, I want to get x to the first over 1.
N minus 1.
Okay, let's see if that works. So if I put in n minus 1 there, and n minus 1 there. If I plug in 2, I would get x to the first over 1. That's good. If I put in 1, that would cause a problem because I'd have a 0 in the denominator, but I'm going to fix that. I think it works pretty good from 2 on. So if I put in 3, I'd get x squared over 2. If I put in 4, I get x cubed over 3, and so on. So that works really good from 2 on. So suppose I just say, let's just add the 1 onto it. But I would still need to sort of start at 1. So if I started at 1, that would be 0, that would be 0. If I did, well, I tell you what, if I separate it like that, and I say 1, plus x to the n over n. All right, I'm just fit. This is how you do this, guys. You futz around with it for a little while. I've got the 1. I need the x to the, there's 1. I could say 1 and then just sort of start my sequence here. 1, 2, 3, and that would get all of them. That's the easiest way to do it, I think. 1 plus x to the n over n. So if we wind up with 1, I'll have 1 plus, and then I'll look at, does that work? Now I'm doubting myself here. How could I do this? N plus 1 over n plus 1. That's not going to work because it's going to add an n. I could do it like this. Now I can do it like that. Remember, you got to be able to plug in n equal 1 and get what you need. So if I plugged in this, the first term would be 1 plus x over 1. That wouldn't work because I want the first term just to be 1. Let's try something else. And this is, I'm not great at this either. I just have to look for the pattern. I'll try this. I still think it's x to something over something that has to do with n. And this has to do with n. Now here's why it doesn't work. Here's why this one doesn't work, because it doesn't work for 1. If you put in 1, where would the sequence start if you put in 1 for n?
At x.
At x instead of 1. So what you want to do, what could give us a 1? So x to a 0 power. So let's try this. The n's and the 1's don't have to be necessarily the same here. Suppose n equal 1 here. But I'll try that anyway. That's still not going to work. All right, let's see. Anybody got any suggestions for me? You see what I'm trying to do? So if I put in 1, that would make that work because x to the 0 would be that, but it would make that not work. All right, I'm gonna leave that as a question mark and let you guys play with it. Let me play with it too. See if you can figure out where that came from. If I were allowed to start a sequence at 0, that would work, and later on I will be, but not right now. One more. Guys, do you see a pattern? Can you tell me what the next number in that list is going to be?
11.
If you say it's going to be 11, then you see the pattern. Say to me what the pattern is. Every time, what do you do?
Add 2.
Looks like you're adding 2 every time. So that's kind of how we want to set it up. I would say when I get 3, I want to add, I start with the first one, which is 3. The next one will be 3 plus 2 times 1. The next one will be 3 plus 2 times 2. Notice I'm getting the 7. Then 3 plus 2 times 3 would give me the 9. That's kind of the pattern I'm looking at. However, I've got to, again, I'm in the position of having to do that first term. So I'm going to suggest something to you and let you look at it. Let's see how much room I got down here. Let's do it down here. I think if I look at that pattern, 1, 2, 3, and I do it this way. Suppose I said 3 plus 2 to the n minus 1. I'm adding 1 every time, but if I started at 1, notice what would the first term in the sequence be if I put a 1 in here?
3.
3, that's what I needed. If I put a 2 in here, 2 times 2 minus 1 would be 3 plus 2. That would be the 5. If I put a 3 in here, it would be 2 times 2. And that plus 3 would be 7, and so on. I think that one's going to work. And honestly, watching somebody else do it is probably not the best way to learn it. Play around with it. So I've given you a few tonight on the homework to play around with to see if you can figure out what the pattern is and how you're going to write the pattern in terms of getting the sequence. Okay. All right. Questions, anybody? So that's a little, so we sort of left this one open. Figure out what you can do with the powers maybe to fix that. And we'll come back to that one. Look at the ones on the homework, and I'll give you the solutions to the ones on the homework tomorrow. Okay. All right. You know, I had a student one time that, good student, looked at these things and she said, my mind just won't work like that. Okay. But it has if you see the pattern and you sort of figure out how your ends have to interact with each other, you get better at it. Okay. So I gave you, here's what I gave you. Again, this is typed up on the sheet on Moodle. There's one. I think you can tell me what comes next in the list. What comes next in that list right there, guys? 1, 4, 7, 10, 13. So they all differ by 3. So this one is interesting because it looks kind of like one we already did. This one looks like it might be powers of, some kind of powers of 2, some that drop and some that don't. That one I'm going to let you look at. That's a pattern that if you've probably seen this pattern in high school. 2, 6, 24, 120. Does anybody know what the next one's going to be? Anybody know what the next denominator is going to be? All right, I'm going to give you a hint, guys, and let you look at this. Do you know what that symbol means in math?
Factorial or something like that.
Say it again, Tiara.
Factorial.
Factorial. Guys, factorial means to take a number. Okay, if you hadn't seen this before, factorial means to take a number and start with that number and count down to 1 while you're multiplying. That's what 7 factorial means. If you've got your calculator with you, take it, get it next to you, and I'll tell you where the factorial is. There's a key that'll compute that thing for you because it really is important. It's going to be important to us. If I put in the number 7 to my calculator and I hit the math key and I go across, there's a menu across the top to PROB, which is probability. This is used a lot in probability. And I look at the menu down below it. You'll see an exclamation point in there somewhere. In my menu, it's number 4. When I hit enter, it'll put the exclamation point behind 7. When I hit enter again, it'll tell me that that's the number 5040. Is there, if you don't, has everybody got a calculator with them?
No.
You don't have one, Alexis? Okay. So here's, bring it back, be sure to bring it from now on, okay? So, and you'll need it to look at this one. So here's what I said to find factorial. Just put in a number. If I wanted to find 8 factorial, I'd hit 8. I'd then hit the math key. Under that, I'd do prob. Then I'd find the exclamation point, and then I'd hit enter, enter. And that'll give me what that is. Okay? So did everybody bring their calculator home with them? Has everybody got access to one? Everybody? Okay. All right. So that's actually going to be, so figure out if you can, see if you can figure out what that pattern is right there. It has something to do with factorial. Okay. All right, guys, I'm done. Try these limits back again in that section 11.1 and see if you can find the pattern going in these things to generate the sequence that generated, or the nth term that generated those numbers right there. And it's sort of a rehash of some of the stuff you already did over the weekend, okay? Did anybody have a question of the stuff over the weekend? some of it you couldn't do, so it's kind of hard for me to, for me to see if you really didn't understand something or we just hadn't gotten to it. Okay, Alexis.
I just don't like this stuff. Like, I know, like, this stuff right here is gonna have me.
When did you do it before?
Like, my junior year in high school. Like, that's the last time I did this stuff. And I
Was it
did
like-
not do very good.
Was it like Math 3 or something like that? Is that what?
Yeah, it was like functions and modeling. And when we got to
Yeah.
this section,
Yeah.
this was the section I struggled the most in. Because
Okay.
I don't see patterns ever. Like,
Okay.
I just don't see them.
All right. Well, I mean, we won't always have to see the patterns. The patterns most of the time will be given to us. Okay. But just play with it. Just pretend it's like a puzzle and you're trying to get better at doing the puzzle. I don't know. Like I said, I'm not that great at it either. I can't. Some people could just adjust it and immediately see what it is. But try it and see what happens. We'll come back to these tomorrow. I'll give you the answers to these, and we'll figure out that other one that we didn't quite get. Okay. So homework is in 11.1. Let me check something, guys. Yeah, that's all that's in 11.1. I think that's all that I wrote there. Yeah, it's all typed up in the assignment sheet. And by the way, I could not write like in the C right here. Dang it, hang on. In that C, something like this, on your homework sheet, I couldn't do a dot. It looked like a decimal, so 2 times 3. So I wrote it as 1/2 times 3, okay? That X is a times, not a variable. So that's what it looks like when I typed it up. Okay, I could find, if I looked harder under symbols, I could have found it. But anyway, there it is. It's times. All right. Anybody got a question for me before we leave? Any more classes? Has everybody finished all their tests? Who sent me? I've got Tiara's improper integrals. I got Deborah. I got Alexis. Did I get Alexis? I got Dion's. Did I get yours, Deborah?
I sent it today.
You sent it to me. Okay, today. Okay, I just hadn't looked, so I saw the ones that had been sent before. So I'll get that. I'll try to get that graded tonight and get it back to you, and then we'll pick this stuff up tomorrow. Okay. All right. I will see you tomorrow at same time, same place. Write down the whatever it is, password. I keep saying I'm going to redo it so the password automatically enters, but I'm scared to death I'm going to screw everything up about the recurring schedule. So, all right. See you later.
Mhm.
Bye.